Hi, my name is dr. Ahmath. In this video lecture, we're going to talk about the matrices. So I've decided to start the course with talking about the matrices because we need to redefine and redenote all of the notation for the vectors. So we are going to talk about the definition of the matrices, some notation of the matrices, some small operations, everything which is required to define the vectors and operations with the vectors. And then later on, we're going to learn about the vectors, and then we're going to go deeper into the matrices and the operations with the matrices. So let's first of all define a matrix. So any matrix is a two-dimensional table, simply. So a matrix is a 2D table. Okay, so we are going to denote the matrices using the rectangular brackets or this kind of curved brackets. Okay, so you can't really put the absolute value, like just the two vertical lines, in order to define the matrix, because that means that something different. So either the rectangular brackets, either the round brackets. Okay, so every element, it's really important for us to define the coordinate system of the matrices. So since it has so every element of the matrix has its own coordinate or own location. So usually in matrices have the number of the rows and the number of the columns. Okay, so for example, if you're given the A in this notation, like n by m, it means that this is the matrix with with n rows and m columns. Okay, so rows are always coming first. So this is going to mean that this matrix has n rows and m columns. For example, if I would like to say that, hey, A is going to be like 2 by 3 matrix. So it means that it's going to have 2 rows and 3 columns. For example, the A might be defined as like 2, 3, 4 minus 1, 2 rows and 3 columns, and 4 and 12, for example, right? So it has basically 2 rows and 3 columns. Okay, so this is going to be 2 by 3 matrix. So the rows are always coming first. So it appears every element inside the matrix also has its own coordinate system, right? So I'm going to write this down now. So the A is going to start the elements like this. So we usually denote the big capital Latin letters as matrices. Usually, like if the matrix has more than one column and more than one row at the same time. So here I'm going to denote the elements. So A11. So it means that this is just the element of the matrix, which is located in the first row and first column. Then we're going to go like A12, so A13, and so on, A1M, right? So it has M columns. So let's assume that A is given as the matrix with n rows and m columns. Okay, so then the second one is going to start A21. So since this element is located on the second row and the first column, right? So the A22, A23, and so on, A2M. So and so on. And the last row is going to start A N1, A N2, and so on, A N M. So in general, A, I, and J is an element on the I's row and J's column. So in general, it's not so difficult. So again, so you see, so the first index means the row number, and the second index means the column number. Okay, so if I will just write down the matrix, so let's say A is going to be some matrix which is like 3 by 4. Okay, then I'm going to write this like it should have 3 rows and 4 columns, like a 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it has 4 columns and 3 rows. So if I tell you what is the element like with the index 3 and 4, so what you need to do is you need to go to the third row, right? And fourth column. And then you need to like get this entry item or element which is located in this intersection of that particular row and the column, which is going to be 8. If I say, hey, what's A1, 2, then you're going to say that this is going to be 4, right? So the first row and the second column. Or A3, 1, it's going to be 5, which is going to be the fifth, which is going to be the third row and the first column, and so on. So this is how we need to basically orientate inside the matrices. So a matrix has a dimension, like the number of the rows and the number of the columns. And every element inside the matrix also has its like own geosystem, right? So basically, it's usually every element of the matrix usually comes with the 2 indices. First index means the row where it's located, and the second index means always the column where it is located. So the reason why we decided to introduce the matrices first is to define the vectors. So throughout this course, in order to make all our notation uniform, like so that we're going to have the uniform notation for the matrices, uniform notation for all the vectors, we are going to define the vectors as the one column matrices. Okay, so a vector, so in this course, in linear algebra, a vector U is a one column matrix. So basically, if you remember, we are going to denote the dimensions of the matrices. Like in the first, it comes the number of the rows, right? So it's going to be n, and the second, it comes the number of the columns. So it's going to be n by 1 matrix. So in general, you're going to define U as U1, U2, and so on, UN, where U1, U2, and so on, UN are just some real numbers. So if I say, hey, a vector U is like 3 by 1, then you're going to say that U is going to be equal, for example, like a 3 minus 1, 4. Okay, so whenever we say that, hey, U is a vector or V is the vector, we mean that it's one column matrix. Okay, so 4, 5, 6. But at the same time, naturally, you might ask, like, why don't we just denoting the vectors as just one row vectors, right? So, okay, so the reason is I would like to always have the uniform notation. So whenever I mean the vector, then this should be a column, okay? Then it's going to be easier for us to make our calculations. Okay, so what do I mean by the calculations? So we need to learn how to add and how to multiply two vectors, okay? So how to add and multiply the vectors. So we are going to come back to the multiplication and the addition of the matrices. So especially the multiplication of the matrices is a little bit difficult. It's not so straightforward. But here we are going to just define addition and multiplication of the vectors, because so far we just need to deal with these operations. Okay. So if you are given two vectors, so let's discuss about the addition. So let u and v are two vectors which are n by 1. So please know that if I would like to add two vectors, they should have the same dimension. So they have the same number of rows, the same number of rows. Since we know that any vector has one column, then let's say u is going to have the elements like u1 and so on, un, and v is going to have the elements like v1 and so on, vn. Then u plus v is also going to be a vector with the same dimension, with n rows and one column. And the resulting vector is going to be u plus minus v is going to be a vector where I would just like to do this operation with every corresponding element of the vectors. So basically u1 plus v1, u2 plus minus, v2, and so on, un plus minus vn. Let's do a couple of examples on the addition and subtraction, which I think is really straightforward. So let's say u is given as 3 minus 1, 0. V is given as 6, 7, 8. So if you would like to add the u to the v, it's going to be again a vector with 3 rows, where I just need to add the two corresponding elements. It's going to be 3 plus 6 minus 1 plus 7, 0 plus 8. So if you would like to subtract, we're going to do these things in the same manner. It's going to be 9, 6, 8. Okay, so everything is straightforward so far. So the problem arises when we will multiply these two vectors. Okay, so the second is multiplication. Okay, so now it appears that if u and v are two vectors with the same dimensions, I can't really multiply u to the v. So if you are given two vectors with n tuples, like basically with like two components, then you can multiply them as a dot product, right? Here for the matrices, we can't really multiply u to the v. Okay, so there is no dot product or the cross product and so on in the matrices. There is just a matrix multiplication, and we can't really multiply them u to the v, because there are certain rules of matrix multiplication. So we need to multiply u so-called transpose to the v, or u to the v transpose. So what do I mean by transpose? Transpose means that you're going to write down every column as the row, or every row as the column. So if you are given u with the components u1, u2, and so on, un, then the u transpose is going to be whenever you're going to write down every column as a row, right? So it has just one column. Then if you transpose this, you're going to have just the one row, u1, u2, and so on, un. Okay, at the same time, the same applies for the v. So if you're given v, like a v1, v2, and so on, vn, then a v transpose is going to be equal to v1, v2, and so on, vn. Okay, so if I would like to multiply two vectors, then I can multiply the u transpose to the v, or either u to the v transpose. So you may tell me, hey, so is it possible to multiply v transpose to the u? I would say yes, and they are the same. So is it possible to multiply v to the u transpose? Yes, in that case, they are going to be different. So actually, you see, so this transpose is either in between of these two vectors, either at the end. Okay, so the transposition should always take a role in the multiplication of the two vectors. It's superbly important. You can't just multiply the two vectors. So if you would like to multiply the u to the transpose to the v with the following, so with the above components, it's going to be a scalar. So the number is going to be just one real number. And we are going to obtain this by just in this way. So it's going to be u1, u2, and so on, un, multiplied to the v1, and so on, vn. So this is going to be the multiplication of this element to this one, u1, v1, plus this one to the second, u2, v2, plus and so on, plus un, vn. Okay, so the u transpose is a v, and the v transpose is a u are essentially the same numbers, the same results. So let's check this. So by the formula, it's going to be v1, v2, and so on, vn, because I'm transposing the v vector, right? And I have to multiply this as a u, u1, u2, and so on, un. And if I now multiply them, it's going to be again v1 to the u1, v1 to the u1, plus v2 to the u2, plus and so on, plus vn, un. Okay, so you see this two results are the same. So it doesn't really matter how you're about to, like, unless the transposition is in between the two vectors, you're going to get the same result. So this multiplication is important for us. It is nothing else as a scalar multiplication. If you remember, if you would like to multiply the two vectors as a scalar multiplication, we used to multiply the corresponding components and then just add them. The same as here. Say we're multiplying the first component of the first vector to the first component of the second. Then second component of the first is the second component of the second, and so on. Then at the end, we're just adding. So this type of the multiplication of the two vectors is called as an inner multiplication. Inner vector multiplication. Okay, so basically we say that, hey, let u and v are two vectors with the dimension n by 1, with the n rows in one column. Then u transpose to the v, or v transpose to the u, have just dimension of the r, a real number, just 1 by 1. Or if you want, you can just write this 1 by 1. Okay. Good. So let's do an example. So let's multiply a couple of vectors. So example of the inner multiplication. Inner multiplication. Okay. So let's say you're given u was the components 2, 1, and v was the components minus 3 and 4. So if I would like to multiply these two vectors, I need to use the transposition, either in the middle of them, either at the end. It's going to be u transpose of v is 2, 1 times to the minus 3 and 4. Then if you remember what I need to multiply the component-wise, basically 2 times to the minus 3 plus 1 times to the 4, it's going to be minus 6 plus 4, which is minus 2. So if you don't trust me, we can just check what is the v transpose to the u, which is going to be minus 3, 4 times to the 2 and 1. In this case, again, I'm going to multiply everything component-wise. So minus 3 times 2 plus 4 times 1, which is going to be, again, minus 6 plus 4, which is equal to the minus 2. So you see, it doesn't matter how you're multiplying the two vectors. U transpose to the v or v transpose to the u are going to give you the same, essentially, numbers. So what about the second multiplication? If you remember, we used to have the second type of the multiplication, which was like, let you are given u and v with the dimensions n by 1, right? So with the same dimensions, actually. Then u v transpose is going to be a matrix with the dimension n by n. Is a matrix with the dimension n by n. Okay, and this multiplication we usually call as the outer multiplication. Outer vector multiplication. So you are not really required to understand the outer vector multiplication right now, since we're going to talk about the matrix multiplication. Then we'll come back probably to the outer vector multiplication. But now I'm just going to give you just an example so that you have an idea what does it mean and how we are actually getting the vectors, getting the matrices by just multiplying the two vectors. Again, if you remember, we've got this just example, 2, 1, minus 4, and 3 and minus 4. So let's say U is 2 and 1, and V is 3 and minus 4. 3, is it like minus 3 and 4? Minus 3 and 4. So if you multiply UV transpose, it is going to be like a 2, 1 times to the minus 3 and 4. So it's going to be a matrix. Basically, you're going to multiply this like first element of the first vector to both of the elements of the second vector. It's going to be basically minus 6 and 8. Then what you need to do is you need to take the second element of the first vector and multiply this to the both of the elements of the second matrix or second vector. It's going to be minus 3 and 4. So you see, so this is going to be 2 by 2 matrix. So let's multiply V to the U transpose. It's going to be so minus 3 and 4 times to the 2 and 1. Again, if you remember the idea, the algorithm is like one element of the first matrix vector is going to be multiplied to all the elements of the second. So it's going to be minus 6 and minus 3, right? And if you multiply the 4 to both of this, it's going to be 8 and 4. Okay, so which is really similar to this one, right? Okay, so this is going to be again 2 by 2. So could you please tell me what is the similarity, and is it possible to get 1 from the second? Is it possible to get this one from this one? Yes, if you are going to just transpose them, right? So this is going to be minus 6, 8, minus 3 and 4. If you transpose, if you remember that transposition means we are just going to rewrite the rows as the columns, right? Or the columns as the rows. So the first row, which is minus 6 and 8, is going to be written as the first column, which is going to be minus 6 and 8. And the second row, which is minus 3 and 4, is going to be written as the second column, right? So the first row is going to be written as the first column. Second row is going to be written as the second column. That's it. This is the transposition, and this is exactly equal to this one. So what we've learned in this video, we've learned about the matrices, that they are two-dimensional tables. So the matrices always are coming with their dimensions, basically the number of the rows and the number of the columns. Okay. Then we've learned about the vectors, which are always just one column matrices. Okay. And later on, we've learned about the multiplication, so the addition of the two vectors, which is straightforward. We're going to just add them or subtract them element-wise. And we've learned about the multiplication of the two vectors, like the inner multiplication, when we're going to get just the constant as a result, or the outer matrix multiplication, when we're going to get a matrix by just multiplying the two vectors. So in our next videos, we're going to talk about the vectors in more details and are going to use the matrices in order to denote the vectors.